All right, hello, physics class. Welcome to week 2 of learning virtually. This is a review day. If we'd been in class, we'd be getting ready for a quiz or more like a quest. At this point, we are going to skip that. So this is still going to be a review day. With the craziness and spring break, it's good to have a good review day. So today's just going to be a review day, and yeah, we'll go from there. Okay, so like I said, this is a review day. I'm going to go through some review. We're going to look through the worksheet you did, hopefully for last class, as well as just some review topics. All right, here's a homework check. I would highly suggest writing this down in your notebook, trying it on your own, do it as an example problem, and then wait and see what my answer is. So go ahead and try that. Pause. So here's my solution for this. So we have two waves. So what we're going to do is write everything we know about the two waves. So the one wave, it says we have a wavelength of 0.328, and it has a frequency of 47.5 hertz. That's what we know. The second wave, we know, has a certain number of waves, a certain number of oscillations that happen in 50 seconds. So we'll write that down. So what does that tell us? Well, if you remember, if we have number of waves and we have time, we can use frequency equals number of waves over time to figure out that the frequency of that second wave is 29 hertz. Well, how does all this help us? How can I find out the wavelength of the second wave? The key on this one is that it says that the wave is going through the same medium, meaning that all mechanical waves that go through the same medium have the same speed. Everything will have the same speed. So therefore, the velocity of wave A has to be equal to the velocity of wave B. That's the key point. And then from there, we just substitute our rule for our speed. Speed of wave A is wavelength times frequency, and speed of wave B is wavelength times frequency. And since they're equal to each other, we just set them equal to each other. And then from there, it's just a matter of substituting everything in and solving for our second wavelength. But like I said, the key on this one was the fact that they are the same medium. So that is the key. All right, here's the worksheet that hopefully you worked on yesterday, or last class, I should say. So the first thing is measure the wavelength. If you didn't get a chance to print it off, I guess you really had a hard time measuring it, but I got 6.1 centimeters when I measured it. And the amplitude is from this baseline, from this equilibrium line to the top of the wave, the crest of the wave, and I measured that to be about 1.4. Kid on the playground, swinging back and forth, goes to and fro each 2 seconds. Well, remember, frequency is number of waves over time, so that would be 0.5 hertz because it'd be 1 over 2. And the period is the time over the number of waves, so that would be 2 over 1, which would be 2 seconds. All right, now we have complete these statements. The period of a wave, the period of a 440 hertz sound wave is, and you just use your conversion. And then the second one is it says that you're on the shore and that they're 8 seconds apart. What's the frequency? Well, it'd be 1 over 8, so 0.125 hertz. So then we got a mosquito that has a buzzing noise, and it's buzzing at 60 beats per second. Well, beats per second is another way of saying frequency, which would be hertz. And so what is the wavelength? That's the length of the wave. If we assume that the speed of sound is 340 meters per second, well, we use our good old speed of a wave equation, and we solve for wavelength. So that was the first side. Second side, machine gun fires 10 rounds per second, and the speed of the bullet are 300 meters per second. What is the distance in the air between the flying bullets? Well, the time period that each one is going off is one second per 10 rounds. So that means the time that between each fire, each time the gun fires off, would be 0.1 seconds. If they're going 300 meters per second, then that means each one is going to be 30 meters apart, just using a regular distance equals velocity times time equation. What would happen to the distance between the bullets if the rate of fire is increased? Well, if the rate is increased, they're going to be closer together because they're going to be happening more often, so it's going to be closer together. So consider a wave generator. That's like the standing wave thing that we did in class. Speed of the wave would be 300 centimeters per second. And the question is, what is the wavelength of the wave? Well, just using our handy equation, we can calculate that it would be 30 centimeters. What would happen to the wavelength if the frequency of the pulse is increased? Well, remember, through the same medium, velocity stays the same, so that 300 would have to stay the same. So if the wavelength is increased, then the frequency has to do the opposite, so it would have to decrease. So the bird at the right watches the waves pass by. If the portion of a wave between two crests passes that pole each second, it means 1 meter has passed that pole each second, so it's going 1 meter per second. What's the period? Well, if that section is going by 1 each second, then that time period is also going to be 1 second. Number 8, if the distance between crests in the above equation were 1/2 meter apart and 2 crests pass the pole each time, what would be the speed? Well, if it's a wavelength is 1/2 and your frequency is 2 per second, so that'd be 2 hertz, so it would be 1.5 times 2, which would be 3. And what would be the period? Well, it'd be the inverse of your frequency, so it'd be 1/2. Right, then we have the Doppler effect. Question about the Doppler effect. So when an automobile moves toward a listener, the sound of its horn seems relatively high. All right, when it's moving away, then it seems low. The change in pitch of the Doppler effect is due to the change in its frequency. The wave speed is still going the same because it's going through the same medium, but the frequency is going up or down depending on which way it's going. All right, so let's look at some review. So what I would suggest doing is I will put the title of what I'm going to talk about up, and I would maybe pause just to think about, do you remember what each of these things are? And then I'll go through. So the first one is comparing period and frequency. Do you remember what those were? All right, period is the amount of time that it takes for each thing to happen. And frequency is how many things happen per second. Time period is measured in seconds and frequency is measured in hertz. And since they're just inverses of each other, then you can find each other by just multiplying by the inverse of each other. Second thing is simple harmonic motion. Do you remember what that was? Simple harmonic motion is anything that repeats itself over and over and over again. And if you were to graph it, it would create a sine wave if you graph the position versus the time. All right. Then we talked about period of a mass on a spring. We had a special equation for that. Do you remember what that equation was? Now, if this was a quiz or test, I would give you this equation, but it is good just to have it in the back of your head. So, period is 2 pi times the square root of the mass over k, which was the spring constant. So as a reminder, spring constant is newtons per meter, and that's going to tell you how strong or how weak that spring is. And that can be anything. That can go from anything from 1, which is like your pen, which is spring in your pen, all the way up to ones that are on like big massive trucks that are in the thousands. All right, then we had period of a pendulum, and that was very similar to the period of a mass on a spring. That was 2 pi times the square root of the length of the string over gravity. So those were the two main equations for physical objects that move back and forth. Right, then we had 2 types of waves, transverse and longitudinal. Do you remember what those were? All right, here's a rough drawing of the 2 of them. The one on the left is the transverse wave. And remember, the wavelength is from crest to crest or trough to trough. The top of the wave is called the crest. The bottom wave is called the trough. And the distance from the equilibrium to the top or the bottom is the amplitude. The line down the middle is the equilibrium. Longitudinal waves are all those waves that kind of look like an accordion or a slinky. All the smashed up parts are called the compressions. All the stretched out portions are the expansions. And wavelength is the distance from one clump to the other clump. Then we talked about wave speed. All right, do you remember what the wave speed equation was? All right, real basic, just wavelength times frequency. And if you think about it, it was the distance, wavelength, times frequency, which is the inverse of time. Because normally it's distance over time, so frequency is the inverse of time. Then we talked about superposition. It is not the location of Superman's secret base or Superman's current location. Superposition is when you have 2 waves that come toward each other and make a bigger wave and then go on their separate ways. And we had 2 types. Remember, there are 2 types. Do you remember the 2 types of superposition waves? We have constructive and destructive waves. Constructive and destructive waves. All right. Constructive waves are waves that move toward each other and are on the same side, meaning the top or the bottom. So the one on the left here would be constructive. You have a 2 and a 5 moving toward each other. When they collide, they make a 7. And remember, they pass through each other. So the 5 would keep going to the left and the 2 would keep going to the right. Destructive waves are waves on opposite sides. So the 4 on top and the -1 on the left, when they combine together, they would make a 3. Simple math. +4, -1, then you'd get a 3. And then they continue on their way. The 4 would keep going to the left, and the -1 would keep moving to the right. Then we did our standing waves. That was the simulation we did, or the lab we did, with the waves that made the bubbles that kind of look like they're standing still. So a couple things about that. Remember, one bubble is what we call the first harmonic, or the fundamental frequency. And because it's only one crest or one trough, it's only half of a wave. And it's the fundamental one, so it's the first frequency. The second fundamental is when there's two bubbles, and it's going to be double the frequency of the first one. And it's one full wave because we have one full wave. We have one crest and one trough. So it'd be one full wave. Third harmonic, continuing that pattern, it's 3 times the original frequency, and the wavelength is 1.5 because there's one crest. Well, there'd be one full wave and then a half a wave. Don't forget about nodes and antinodes. Nodes are all the knots, all the dots in between them, and then the antinodes are all your amplitudes. Okay. That is all I really had. If we were in class, we would have done some more little activities. You would have done the worksheet that I assigned on classwork. So there are 2 things for you to do on the classwork tab. The one is a review worksheet, which I will go over next class, which I'll post on Wednesday. And then you have the other worksheet, just the regular homework that's right here. So if you have questions, go ahead and just drop those to me over email, and I will send out a blast about my change to how I'm going to do Zoom meetings. So look for that. Talk to you later.